Hi, my name is Ramiro, and I'm an electrical engineering student here at The Ohio State University. Today I'm going to show you, in 4 simple segments, how to detect your pulse using infrared light. Let's go get started. Now before we begin, we're going to need the following items. For this experiment, most of the parts were purchased from digikey.com. To start, we will need an infrared light emitting diode, a photodiode, a large clip, one that could accommodate a person's finger. I used OXO Softworks. A machine screw. I used a number 6, 32 threads per inch, 1 1/4 inches long. Test leads with alligator clips, heat shrink or electrical tape. We will also need a breadboard, 2 operational amplifiers. I recommend LM358N IC chip, which already has 2 operational amplifiers, quarter or half watt resistors, a pair of 10 kilo ohm potentiometers, a pair of red light emitting diodes, a 9-volt battery and connector. We will also need a power drill, a glue gun, a soldering iron, a cell phone with a digital camera or a digital camera, a flathead screwdriver, and a black marker. Now, as I previously mentioned, we're going to use infrared light to detect our pulse. Therefore, we need to create a source of infrared light. And this is easily done by using an infrared light emitting diode or infrared LED. They're easy to use because all you need is a battery, the infrared LED, and a resistor. Photodiodes behave just like solar panels in that they take ambient light and transform it into an electrical current. In our experiment, this electrical current carries the signal that we're looking for, in other words, the human heartbeat. But because our project requires that the photodiode focus only on the infrared light, we need to minimize the occurrence of ambient light. How do we do this? The best way to block out ambient light is to use a black marker to cover up the top, the back, and the bottom faces of the photodiode. And here's what the diode should look like after it's been colored. Now that we covered the photodiode and the infrared LED, we need to use a clip to be able to attach them securely onto your finger. But before we assemble the clip, we need to prepare the items, the necessary components to be able to build the clip. First, drill 2 holes on the same leg of the clip. One hole will be 3/32 of an inch for the machine screw, and the other one will be 3/16 of an inch for the infrared light emitting diode. However, adjust the diameter accordingly if you use either a wider or narrower screw or LED. Next, we will prepare the photodiode. Strip 2 pieces of wire so that they may be soldered onto the anode and cathode of the photodiode. After soldering the wires onto the photodiode, use either shrink wrap or electrical tape to isolate the terminals and to prevent a short circuit. Now that we've prepared the parts for the clip, we can start putting the clip together. First, screw in the machine screw onto the clip. This will help adjust the pressure on the finger and will also help keep the clip open to facilitate the glue-in of the photodiode. Next, place the infrared light emitting diode in the other hole and apply glue liberally. This will keep the diode in place. Next, open the clip as much as possible and glue the photodiode to the inside of the other leg of the clip. Now we can connect the battery, the infrared LED, and the photodiode to the breadboard. First, connect the 9-volt battery connector to the breadboard. Remember to connect both rails to the battery. positive to positive, and negative to negative. Now we will connect the light emitting diode to the breadboard. The light emitting diode will be forward biased. In other words, we will connect the anode to the positive voltage rail of the breadboard, and the cathode will be connected to a 100 ohm resistor connected to the negative voltage rail of the breadboard. But how can we tell the difference between the anode and the cathode on a light emitting diode? Simple. When you look at an LED, the longer lead is the anode, and the shorter lead is the cathode. And what if you cannot tell the difference from the length of the leads? The best way to tell the difference is to look at the bottom of the plastic case. If you look around the bottom of the plastic case, you will find the flat spot indicating where the cathode is. But for now, let's make the connections for the light emitting diode. Start by connecting a 100 ohm resistor to the negative rail of the breadboard. Then, make a direct connection to the positive rail of the breadboard. This will be connected to the anode of the infrared LED. Then, make a connection between the cathode of the infrared LED and the 100 ohm resistor. Afterwards, we will connect the photodiode. However, the photodiode will be reverse biased. In other words, this time we will connect the cathode to the positive voltage rail of the breadboard, and the anode will be connected to a 100 kilo ohm resistor connected to the negative voltage rail of the breadboard. However, since the human eye cannot see infrared light, how do we make sure that the infrared light emitting diode is working? Simple. Because this video is being captured with a digital video camera, you the viewer are able to see when the infrared light emitting diode is working or not. However, if you don't have access to a digital video camera, you can always use the viewer of either a digital photo camera or a cell phone with a digital photo camera. Now that the clip is assembled and we have an electrical signal coming in from the photodiode, we need to amplify the signal. How do we do that? We use an operational amplifier, or op-amp for short. Op-amps are known as the workhorse of analog circuitry because, depending on how they're configured, they can be used to fulfill many different tasks, which is why we chose the LM358. The LM358 is a low-powered amp. What does that mean? It means that we can use a 9-volt battery to be able to run the LM358, which is not always the case for all operational amplifiers. And second, the IC chip has exactly 2 op-amps, which is exactly the number of op-amps that we need to run this circuit. As I previously mentioned, for our circuit we will be using 2 different op-amps and 2 different configurations. The first op-amp is going to be configured to be an amplifier with variable gain, and the second one will be configured as a comparator. But for now, let's go back to the lab and I'll show you how to set up the LM358 op-amp. Place the LM358 IC chip on the breadboard, but before making the connections, let's first review the schematic of the LM358 IC chip. We will first make the connections that will power up the chip. First, connect pin 4 or ground to the negative voltage rail, and then connect pin 8 to the positive voltage rail. Next, we will make connections from the 100 kilo ohm resistor to pin 5, or the non-inverting input of op-amp B of the chip. Next, we will use one of the potentiometers or variable resistors. These will help us control the amount of gain from the amplifier. Start by placing the first potentiometer on the breadboard. Next, make a connection with a 10 kilo ohm resistor from pin 7 of the LM358 chip to the potentiometer. Next, make a direct connection from the potentiometer to pin 6 of the LM358. Then another connection from the potentiometer to the negative rail of the breadboard. This is our negative feedback loop. Now that we can control the gain from the op-amp with the potentiometer, we want to ensure that we have the right amount of gain. In order to do this, we will need a visual aid. We can do this by connecting a forward-biased standard red LED in series with a 330 ohm resistor between the output of the op-amp, or pin 7, and the positive voltage rail. This will indicate how close the output of the op-amp is to the positive voltage rail. How does this work? When the output of the op-amp gets close to saturation, it will approach the voltage of the positive rail. Therefore, there will not be enough of a voltage difference to light up the red LED. Therefore, we need to reduce the gain. When this happens, the red LED will light up. Therefore, we want to adjust the potentiometer so that the red LED is as dim as possible. This will give us the most amount of gain without saturating the op-amp. Now that our signal is amplified, we will use the second op-amp as a comparator to light up the LED to indicate our pulse. We take the amplified, unsaturated signal coming from the first op-amp and send it to the second op-amp. This second op-amp will be configured as a comparator. As the name implies, it will compare two different signals. One signal will come from the first op-amp, and the second signal will be a DC signal that we will create with a resistor and a second potentiometer. Start by placing the second potentiometer on the breadboard. Next, make a direct connection from the potentiometer to the negative rail of the breadboard. And then make another direct connection from the potentiometer to pin 2 of the LM358 chip. Then connect a 2.4 kilo ohm resistor from the positive rail to the potentiometer. Finally, make a direct connection from pin 7 to pin 3. And the final step in the circuit assembly process is connecting the second red LED that will indicate the human pulse. Now that the circuit is completed, let's test the circuit. Place your finger in the clip and adjust the screw so it fits snugly on your finger without being tight. Next, adjust the first potentiometer so that the first LED is as dim as possible. And finally, adjust the second potentiometer so that the second LED starts to flash with your pulse. Now that everything seems to be in working order, let's test the circuit with the oscilloscope. An oscilloscope is a device that displays electrical signals on a screen, allowing us to peek inside the circuit and to see how it works. We are going to compare the two signals as they enter the second op-amp. In other words, we're going to see what the second op-amp sees. When we look at the oscilloscope screen, we will see two different signals. The yellow line is the signal that's coming from the first op-amp, or the heartbeat signal. The pink line is the adjustable DC signal going into pin 2. The second op-amp receives these two signals and compares them. When the heartbeat signal is higher than the DC signal, it will light up the LED. And when the heartbeat signal falls below the DC signal, it will turn the LED off. Well, thank you for watching the video. I hope you enjoyed this presentation. If you want to know more about photonics or analog circuitry, check us out at www.ece.osu.edu. Once again, thanks.